So welcome back. And the topic today is actually to deal with a technicality before we step into density functional theory. And one of these technicalities is something which often is actually hid under the carpet when you derive density functional theory. And that is to rewrite the expectation value of the energy in terms of the density. So when you look into textbooks, you will often just see the expectation value of the energy written out in terms of density. And then you ask yourself, where do these expressions come from? Because till now, we have been looking at the functional of the trial wave function, or the wave function if somebody gives you the exact wave function. And then we have calculated the expectation value of quantities with respect to the wave function. Now, what is the difference between density functional theory and the standard approach, which we have seen till now with Hartree-Fock, et cetera, is that we are now going to use the density. We use the electron gas as a kind of stepping stone towards density functional theory, because you saw that you could express the kinetic energy as a function of the density of the system, the number of particles divided by the volume, and we could also derive the interaction energy in terms of a function of the density. And that went like the density to the power of 4 divided by 3. The kinetic energy runs like density to the power of 5 divided by 3. And these expressions, which we then got by looking at the infinite electron gas, a homogeneous system. So how do we actually express the energy in terms of the density? So let's look at some definitions which we need to carry with us, and then see how we can actually rewrite the Hamiltonian and its expectation value in terms of the density of the system. If you can do that, then we are ready to discuss the two theorems of density functional theory. Okay, so this is roughly the strategy. And we are going to use the lecture today to simply rewrite the energy as a function of density. So when we have the energy as a function of density, that's when we can start looking at the theorems of Hohenberg and Korn. Okay, so this is a technicality that's actually needed. And as I said, if you dive into any textbook on density functional theory, they often just simply state this is the expression for the energy. And then you ask yourself, where does this come from? So let's try to understand it. And in the lecture slides, if you then scroll down and go beyond the electron gas, which is what we covered yesterday, and what we found then is that the energy is something which can be written out in terms as a function of density. But then with density functional theory, what is interesting then, when we now set up everything, is actually to rewrite the expectation value of the energy as a function of the density. So what I wanted to do first is to give you some definitions. And then with these definitions, we are going to look at the expression for the energy. So the density here is one body density, is defined as an operator. And that operator is now given in terms of a delta function. And then you can calculate the expectation value of that one, which then defines the so-called one-body density. So this is normally a quantity which would be normalized. So we are later going to see that this will have a factor of n. So that means that when I integrate this one, that gives me the number of particles. Now, there is, if we now look at the more general definition, and that's the one we will discuss a little bit in more detail now. So remember now that what we defined in the very beginning of the semester, we had a collective variable x, which then contains the spatial degrees of freedom and spin. So that was a kind of more compact notation, which we defined in the very beginning of the semester. So this quantity here is normally called the one-body density matrix, and that is obtained by tracing out all the other particles except on one. So you can see now that the definition of it is given in terms of an X prime here. For that particle, you don't integrate out, and X here. So in principle, this does not need to be diagonal. Now, the quantity which you normally use is the diagonal one. And that one is normally called the density of the system, this N. And that's the one which is going to be connected with the number of particles divided by the volume. Because you see now that if I integrate this quantity here, but the definition is so that the one body density matrix is then, when it's normalized so that when I integrate over all of space, this gives me the number of particles. So this definition here is important because you see now that when I do this integral, and then obviously if I divide by the volume, then I have the density which we discussed in connection with the electron gas. So these are just definitions which I'm setting up here. Then there is something which is called the two-body matrix. And this is defined, and we are going to see now in practical terms how these things pop up in the calculations of the energy. So the two-body density matrix is actually defined like this. And the thing is that this is an object which you can then rewrite, and we will see that on the whiteboard notes. You can actually rewrite that one in terms of one-body densities. And that's the quantity which allows you to rewrite, for instance, the direct term of the Hamiltonian in terms of the density squared. Yeah?
Is the density operator connected to your expression as the trace of the Hamiltonian?
Yeah. So it is that. So you have, if you think of more formal ways, you can actually, in a modern quantum mechanics approach, you can actually define it like that. So the density matrix is a very important tool when we are setting up expectation values of quantum mechanical problems. In density functional theory, so I'm going to wait a little bit before we look at the rest here, but let's now look at what we want to show here today, that we can rewrite the expectation value of the energy in terms of this quantity N. Okay? So let's do that. I'm going to switch back to the whiteboard here. So our task, the thing we want to do is, in density functional theory, we want to have the energy as a functional of this density. And in the notation here, I'm going to switch a little bit between X and the vector R. But let's now just write it in this form here. And we're just going to ask ourselves, what does this look like? So if we look at the Hamiltonian of the system, that has a kinetic energy operator, T, which I'm writing like this. Then there is an external potential which confines the motion of the particle. So this is actually an important object, the external potential, when it comes to the discussions of the Hohenberg-Kohn theorems. So let's just write it like this. So this is an operator. And then we have an interaction piece, which then could be the Coulomb interaction. And we could have some additional terms, which I'm just going to call H2 here, which if we are dealing with atoms and molecules, this could actually be the nucleonic degrees of freedom, which we are normally leaving out. And if we follow this Born-Oppenheimer approximation, it's pretty common to leave out that term H2 here. Now, this Vx T here, which we have written down, is something which we typically would write out as a sum over all particles in terms of the external potential, which confines the motion of the particles. So X of I now contains both spin and spatial degrees of freedom. But just remember now that in the beginning of the semester, we defined this one to contain both the spatial degrees of freedom and the spin degrees of freedom. So this is just a compact notation for these common coordinates. So the external potential is typically something like the potential which is set up by the atomic nucleus, which attracts an electron. So if we are just looking at the electronic degrees of freedom, then typically this interaction here could be the Coulomb interaction. So we would have a sum over I and J, and then we have an interaction which typically depends on the relative distance only. So this Xij is then typically Xi minus Xj. This is a pretty common setting. And in electronic systems, this is normally just the Coulomb interaction. And then T is then just our kinetic energies. So we would have a sum over the number of particles, and then we would have minus h bar, 2m, and then we would have a delta I squared. Okay. And we're just leaving normally out this specific term here. Now, what we are going to do now is the following. So we are going to rewrite this energy as a function or functional of the density of the system. So we're going to have kinetic energy, which is going to be a function of density. And we saw that already with the electron gas. And then we are going to have this V external, which is going to be a functional of the density. And we are going to have, so we are going to skip this other term. So this will also be a functional of the density. And then we have another term which we just left out here. And I am typically going to approximate things by not looking at this term here. Okay? So this is roughly what we want to do. Let's now take a look at this external guy. Okay? And let's remind ourselves about the expression when we calculated the expectation value of that. So when we look at V external, so this is the expectation value. This was given by phi 0 or psi. We can just write a general wave function. So we don't need to put a label phi 0, but we could just keep that as a general state. And then we would then have a sum over I equal 1 up to n. And then we have this V external. And then in our specific case, this function was often just a function of the positions. So it's pretty common that the external potential which you have is only a function of the spatial degrees of freedom. You can add spin to it, but let's just limit ourselves to the spatial degrees of freedom. Now, what we did then, when we set up these expressions, if we now just look back at what we had, this is something which is then given by an integral over d. Oh, well, let's just a moment. Let's just keep this as an x here, because then we can make it much more general. So let's just assume that we also have spin degrees of freedom. So then what we had was an integral over dx1, dx2, up to dxn. And then we had the wave function for the system, which is now a function of x1, x2, up to xn, multiplied with the sum over these operators from I equal 1 up to n. And then we have a V external of xi, and multiplied with the wave function x1, x2, up to xn here. So now we haven't said anything about whether these are fermions or bosons or whatever. The other thing which we are going to look at now, we are also going to assume that these wave functions are normalized. This phi or psi or whatever we call them are normalized objects. So this object could be a Slater determinant, or it could be the exact solution of the system. Okay? Now, the other thing which we are going to look at is the expectation value of this quantity here, x. That is given, this quantity which we defined earlier, is given by phi of n, this operator of x, and then phi. And we're assuming that the wave functions are normalized, okay? So I don't need to plug in a denominator with the normalization constant. And this quantity here is then simply given by n, and then we have the integral. This is the same thing which you saw in the slides earlier, of dx2 up to dxn. And this is now given by the wave function phi x1, x2 up to xn squared. So keep again in mind that I have assumed that these guys here are normalized. Yeah. Yeah. 0 on the function here. And no, 0 where? Oh, sorry. This is just my default thinking about the ground state of the system. Sorry, can now just be any wave function, but normally you would pick the ground state of the system. So later we are going to identify this with the ground state of the system. And this density is going to be the density of the ground state. Okay? But now we can just leave this in very general terms, actually. So this is the way we have defined it. And this operator n of x, just to remind you of that one, is simply a sum over all the particles which are in the system of a delta of x minus x of I. Okay, so the quantity which you have here, when you take the integral over dx of n of x, this is simply going to be equal to the number of particles. And that follows immediately from the expression which you have. So let's now look at the expression for this one-body operator. So if we take a one-body operator, what we are going to get then, and keep in mind now that we are making an assumption that this one-body operator which we have here is just a variable of, let's say, the positions. So that means it doesn't act on the state. So that means that I can actually rewrite that one. So if you think of the attraction from the atomic nucleus, that goes like 1 over r, the distance between an electron and the atomic nucleus. So that means it's an operator which actually does not change the wave function. So this is an assumption which we're going to make here. And that means that when I look at this expectation value of phi of V external of phi, that is simply going now to be something which we can write out term by term, because the operator itself is a one-body operator which acts on each particle once at a time. So what we are going to get then is something which looks like this, dx1, there's going to be a dx2 up to a dxn. And then we are going to have the wave function squared, x1 up to xn squared. And then there's the sum over the external potentials, vxt, x1 plus v external, x2 plus v external xn. So this is essentially what we end up calculating. And when we write it out, this is something which looks like as follows. So it's going to be a dx1, and there's going to be a v external x1, and then I have all the remaining integrals, dx1, dx2, up to dxn. And now, plain laziness, I'm just going to write this as phi squared. I don't keep all the quantum numbers there. And then we get a new term where I have the integral dx1, but then I have a dx2 of v external x2 here, and then I have a dx3 up to a dxn multiplied with the wave function squared. And this continues now till the final one, where we now have a dx1 up to a dxn, v external, and then I have the wave function. Now, all these guys here, they're actually nothing but the same integrals, because x1, x2, x3, etc. are just dummy variables. So you see now that what I can do is actually to rewrite this as a simpler expressions because I will have n terms. So I can rewrite this as n, and then they all look alike. So I can write dx vxt of x, and then I have the remaining integrals dx2 up to dxn multiplied with the wave function by x1, x2 up to xn squared. Now, this quantity which you have here, if we now go back to the definition of the density nx, this is nothing but us having dx v external of x times n of x. Does that make sense? If we look back at the definition we had for the density, I mean the diagonal term of the density matrix, if you go back and look at the definition, this is the way we defined it. So actually, now, by the way, I actually made a small error here. This should not be here. Sorry, that was just wrong. I saw that now actually. So if you do that, then you have the definition here of the matrix, the density of the system and the external potential. So we can actually write this as the V external as a function of the density. So that's term one, okay? So we showed now that we can actually write the expectation value of the external potential as a function of the density. So often when you go into textbooks on density functional theory, and I guess, Mariam, I mean, you've been studying density functional theory, and I guess that this is something which you often don't see the derivation of, right? So people would just say, this is what we have. And then it's left to the reader to figure out. So this is actually not so difficult to calculate. The thing which is a little bit more difficult is the interaction piece. Because in our case, this is also going to involve fermions with the anti-symmetry. So when we now looked at the interaction piece, so we want now to look at the interaction piece also as a function of density. Now, what we know when we have used a Slater determinant, so with a plain Slater determinant, then we could write this out in terms of single particle states. But now we're going to break a little bit with that, and we're just going to set up the expectation values here, okay? So let's look at a two-body interaction, and what we would have then, if we think in terms of two particles only. So let's just assume now that we have n equal to 2 here. Now, if we set that up and we leave out discussions about the Pauli principle, the exchange term, what we are going to get then is something which looks like this. So we will then have an integral of dx1 and dx2 here, and then we will be having the wave function of x1, in this case, or x2, and then it's 1 divided if we now are looking at a Coulomb type of interaction. So we are now specializing to the electronic case here. Now, this operator x1 over x1 minus x2 does not change the wave function. So when you look close at this one, you can actually rewrite it in terms of a simpler term. So let's just wait a little bit so people have time to write down. So let's do that. So this would then be equal to an integral over dx1, an integral over dx2, and then we are simply going to have the wave function squared, x1, x2, divided by x1 minus x2 here. This is something which I then could define as if we now look close at what we have here with this dx2 and x1 times x2, it doesn't look like as if we can simplify it further. You could write this term here in terms of a one-body density. If you look at this term times that term, and if I multiply that with n, number of particles, 2 in that case, this could be proportional to a one-body density. But let's look at the case with n equal to 3. So if I have n equal to 3, then what I will get is an integral here over dx1, dx2, dx3. And then I'm going to have the wave function x1, x2, x3. And I'm going to have a summation here over the single particle states. So I will actually get different terms here now because the operator is going to give me one term, which is x1 minus x2. And then there's going to be a new term, which is dx1, dx2, dx3. And now I'm just going to write the wave function like this, x1, x2, x3. And then I have an interaction term which goes like x1 minus x3. And then there's a final term here of dx1, dx2, dx3. And then I have the wave function of x2 minus x3. So now I plugged in explicitly the Coulomb interaction. So what I could define now, if you go back to the Jupyter notebook or the slides for this week, I also defined something which I called the two-body density matrix. So what I'm going to do now is to define a quantity which is going to look like as follows. So this is a two-body density matrix instead of a one-body one, which we saw earlier, where I integrate out all single particle states except for one. Now I'm integrating away only n minus 2. So that means that this guy is going to be defined as dx3 of phi, and then I just write it like that. So that's density. Then I can define obviously 2 of x1, x3, which is then going to be simply dx2 squared. And then clearly x2, x3, which is going to be dx1. So instead of integrating away all but 1, I'm now integrating away all but 2. I can then rewrite my expectation value in terms of these. So that means that I can rewrite that expectation value as a dx1, dx2, and then I have this rho 2 of x1, x2 divided by x1 minus x2 plus, and then I have a dx1, dx3, and then I have rho 2 of x1, x3 divided by x1 minus x3 plus a final one, which is a dx2, dx3, and then I have rho of 2 here, just to distinguish it from the one-body case, divided by x2 minus x3. And now you see that these are all dummy variables. So that means I can actually collect them. And due to the fact that we are having two particles present, what we will get then is a general expression. If we write this out, so you have 3 terms here, but in general, this is going to be equal to, so the general expression is something which we can write out as n of n minus 1 divided by 2, and then I have an integral over dx prime, and then I have this quantity rho of x prime, divided by x minus x prime. And you see that if you put n equal to 3, you have 3 times 2 divided by 2. So that's 3 terms. And that's exactly what we had here, 3 terms. If you're setting up 4 particles, you will get 4 times 3 divided by 2. So that will give you 6 terms, etc., etc. So this factor which you see becomes a normalization factor due to the fact that you have a certain number of particles. Okay? So the only thing I did now when I wrote the general expression is that since all these are dummy variables, I can always relabel them. And this is the expression which we end up with. Now, this doesn't look like the one-body density. Now, there's a result which I'm going to set up here, and that is that if we take n times n minus 1 here, multiplied with this rho 2 of x, so I'm just stating this result without proving it, this can be written out like n squared of, now these individual guys are the guys without the n's. So just pay attention. So I'm putting an n prime here because previously I defined this n as n times something. And this is an n prime of x prime. So if I bake in the n here, then this should just be the same as n of x times n of x prime. But then there is something which comes in addition here, which is a minus, and then n times a Kronecker delta of x minus x prime times this n prime of x. Now, this term disappears when we are dealing with a Coulomb interaction because we cannot have particles x, we cannot be equal to x prime. So that means that for this specific integral, which we have here, like the Coulomb interaction, this Kronecker delta disappears. And then we are left with a term which then simply includes this n times n minus 1, or just, if we use this formula, then what we are going to get then is that this is given by d, dx prime, and then I'm going to have n of x, sorry, not n prime, but x prime, divided by x minus x prime. So this is going to be our direct term, because now we haven't discussed anything dealing with the Pauli principle. So if you think back of what you did when you set up the Slater determinant, that the Slater determinant gives us a kind of exception here. So what we've shown now is that the interaction piece could in principle be written out like this. Now there are some complications. So let's go back to the Jupyter notebook here and take a look at what the complications are. Now, this expression here is also something you can derive if you now assume a Slater determinant in terms of single particle states. So let me just do a small intermezzo here. So if you set up your wave function in terms of a Slater determinant, and then you would have the single particle states. So till now, I haven't made any assumption about the wave function, whether this is an ansatz or it's the true wave function. When you think of a Slater determinant and you have n particles filling in all single particle states up to the Fermi level, so this would be typically then an ansatz for the ground state, but it could be an ansatz for any state, except that then we would not sum from 1 to n, but we would have other single particle states. So this is what we have seen till now. And this goes all the way down to n of x of n. So when I then calculate, and this is pretty straightforward to see, when I calculate this n of x here, which could be n of x1, this is now given as we have defined as the number of particles multiplied with the integrals over dx2, dx3 up to dxn. And then what we would have would be this phi 0 of x1, x2 up to xn squared. Now this reduces to a very simple expression, which is going to be simply the sum from I equal 1 up to n of these single particle wave functions of x1, and then we let x1 go over to x. So that means that this n of x is simply given by the sum over the single particle wave functions squared. So this is what we have been used with till now. But then you have to keep in mind that when we now are looking at the interaction piece, there's going to be a term which arises due to the Pauli principle, the exchange term. So we would have something, if you look back here, which we can then identify. So this term here is normally identified as the Hartree term or the direct term. Because when you set up the Hartree term, or the direct term as we called it, then what we would be doing then is, in our specific case, if we go back here, then these wave functions would then be Slater determinants. And that means that for each one of them on the brass side and the Ket side, I would get a term which is proportional to the density, and then another term which is proportional to the density. So this is something I leave to you as a small exercise to see that if you then use a Slater determinant, then what you will get is a term with a Hartree term plus the exchange term. Okay? So if I plug in this expression here, then if we are thinking of a system of fermions, so for fermions, there will be a term and with a Slater determinant ansatz and an SD ansatz, a Slater determinant ansatz. This interaction piece, V int, as a function of the density, is going to be given by the direct term, which is a Hartree term. And that term is simply going to be an integral over dx and dx prime. And it has a density nx and nx prime divided by the interaction x minus x prime. So this is what we call the Hartree term. Or just a direct term. And this is the equivalent when we deal with a Slater determinant. This is the equivalent of what we have set up of ij of Vij. So just keep in mind that when we set up an expression like that, this expression which you see here, that is based on an ansatz where the wave function is given in terms of single particle states. But you could actually start differently, and the expression which we cooked up here is an expression which in this specific case did not take into account the anti-symmetry. If you do that, then you have to be a little bit careful because there will be an additional term. And in our case, the additional term here, if we now just look at this as an intermediate step calculation, this additional term is something which in density functional theory is just called the exchange part. This is not something which you can write out in terms of what you will call a decomposition of the density, in terms of you have the density x and the density of x prime. So that means that you have a simple density dependence, because if you think back of the to the exchange term, you cannot actually write that out as a product of the two densities. So when you so this would correspond in its simplest term, it would then correspond to what you would have from the Pauli exchange principle or the Pauli principle. But you can also think of this term which comes in here as something which contains more complicated correlation. So the x can then represent the exchange due to the Pauli principle, and the c can then represent complicated correlations. Now, when you think of the electron gas, what we did there was actually to obtain a result for the interaction piece where the direct term was cancelled by the background and the interaction of the electrons with the background. So in the electron gas, this term disappeared due to the background. But if we now look at a system of electrons in an atom or in a metal or whatever, then we would have to deal with this term. And then we have the exchange term. Now, the simplest possible approximation you can make is then simply to replace this exchange term with what you had from the electron gas. And that's the local density approximation. So you could say, in a way, in a nutshell, all of density functional theory deals with finding the best possible approximation to the exchange correlations. So if we bake everything together here, what we have is a model where we have the energy, which is a functional of density. And now I'm going to put here HK, Hornberg core. So this is going to be given by density, kinetic energy. And you saw that this external potential is something which is straightforward to write out as a function of density. Then we are going to have a term, which is the so-called Hartree term, which I'm going to write out like this integral here. I'm going to have a d of x, dx prime, and x prime divided by x minus x. So this has an explicit density dependence plus an exchange part, which has a density dependence, which we don't know. So the simple model, which many of you may have encountered, is called the Thomas Fermi-Dirac model. Have you heard of that one in physics courses? So there's something which is called Thomas Fermi-Dirac. And this is roughly where we will stop today. And then we will use the next lecture and the two next ones to discuss the midterm. So the Thomas Fermi one, in that specific case, this is given by what we had for infinite nuclear matter. No, not nuclear matter, but the electron gas. So this is replaced by the electron gas. And that means that since these are integrals, this is going to be replaced with some constant. So it's going to look like the following. So if we take the results from the infinite electron gas, and in that case, we have summed away the spin degrees of freedom. So we are just getting an integral over d of r. And then we have the density, n of r, to the power of 5/3. So this is what we found when we did the calculation for the electron gas. So this constant C1, if we then go and look up what we got, is 3 divided by 10. And then there's a factor of 3 pi cubed of 2/3. So now we're just taking the result from the electron gas. So that's the first approximation. Then the external term is something which we are just going to leave out there because this can be easily calculated. So what we will get then is, if we now collect everything, well, let me just find my expressions here. I have to find out where I put it actually. Yeah, so we will have the external term, the external, because now we are going to make an approximation where we need to plug in the explicit expression for the external potential. So in the electron gas, this external potential disappeared for the electron gas because that was cancelled by the direct term in the expectation value of the energy. But when we now have a specific system, so suppose a system of atoms, then we are now going to assume that this external potential depends only on the spatial degrees of freedom. You could actually add spin if you want to, but now we are going to leave this just as it stands, because we don't know the value of this V. We don't know what this V of X looks like. This is something which we can specify. Then there is going to be another term. We will have the term. We will also have a term which goes like 1/2, and then we have a d of r, and then a d of r prime, and then we have the densities of r prime, and then an r prime here, divided by the r minus r prime. We also have a normalization condition now, since we are leaving out the spin degrees of freedom. You can add them if you want to. This is given by n. But then we have an exchange term. And the exchange term, EXC, is then given by the results from the electron gas. And this is normally what's called the local density approximation, because being local in density means that it depends only on the density as a function of r. So this term is then given by a constant C2. And then if you look back at what we had for the electron gas, we know that this term went like the density to the power of 4/3. And this term here, we did actually calculate that one. That was given by 3 divided by 4. And then I'm just putting back the constants which we derived yesterday, like that. This is the Thomas Fermi model. So what we need then, in order to find the equations of motion, then we need variational calculus. So let me just write this up, because this is where we are going to start next week. So variational calculus So that means that we are going to use the Euler-Lagrange equations. We are going to put in a Lagrangian, which we will identify as the energy. So variational calculus with respect to the density n of r to find the equations of motion, which in our case is Schrödinger's equation. And this is where we will start next week. So we will use this example here, which is a simpler case, and where we take the results from the homogeneous electron gas and calculate the kinetic energy that way. And we also calculate the exchange energy that way. Then what we can do next is to use the machinery of variational calculus. As you probably remember, when we started with Hartree-Fock, you start with the Lagrangian of the system, you set up the Euler-Lagrange equations, and then you find the equations of motions, which in our case is Schrödinger's equation. So this is exactly the same recipe, except that now the functional of energy is given by this Thomas Fermi functional in terms of density. So this is how we would bake in density instead of the wave function. So the big difference between what we have done previously with the Hartree-Fock theory is that we have been looking at the energy as a functional of the wave function. And then we made perturbations of that. Now we're going to make perturbations around the density and use variational calculus to find the equations of motions. And this is where we start next week. So we will actually pick up this example, and we are going to use variational calculus. We are going to find the equations of motion. Then we are going to look at this in more general terms, and that will define the Hohenberg-Kohn functional, which in that case does not make the assumption that the kinetic energy is given by the homogeneous electron gas. And that's where we will start in deriving the Hohenberg-Kohn theorems. There are two of them, and they're actually pretty easy to prove. They're actually proved by contradictions of in terms. And the proofs are actually pretty simple. And then when we have done that, the problem which we have to face is that we don't know the density. Because if you know the density, you have the exact wave function. But in principle, the theorems assume that if somebody gives you the exact density, then you can say everything about the system. The thing you have to do is actually to make approximations in order to be able to calculate. And that leads into a recipe which is called the Kohn-Sham equations. and the Kohn-Sham equations are going to be Hartree-Fock lookalikes at the end. So the basic calculation recipe is going to be like a Hartree-Fock recipe when you implement it numerically. But in principle, if you know the density of the system, you can actually compute everything. And these is what the Hohenberg-Kohn theorems actually deal with. So it's a very powerful approach if you know the exact density. Okay, any questions? So I thought we could use the next lecture and also the rest of the day to just discuss the midterm. So feel free to come back and forth. There's some cakes here to gain some energy for the rest of the day. Then I'm going to stop the recording here.